hysteresis loss. Already I defined that if you consider that a structure of a schematic structure of a particular rotating machine, that is the field is permanent and there is a armature is rotating coil is there. If you consider a small iron bar, say A, B, and after half cycle, this is the position of AB. Now you see, when it comes, that small iron bar, when it comes under the influence of the north pole, so opposite poles is induced here, and after half cycle, when it comes under the south pole, then you see that it comes under the influence of the south pole. So this terminal, A terminal is north pole is induced, and here you see when it comes under the north, when it present in under the influence of north pole, that pole induced is south pole. So after every half cycle, there is a continuous reversal of the flux in this small iron bar. So amount of energy is spent to required for that flux reversal, and that amount of energy you can say that is dissipated. So that is basically the hysteresis loss. So now we have to find out that expression of the hysteresis loss. So for per cycle of the magnetization curve. So for that purpose, say suppose if you consider a sorry. Just you consider a iron bar, okay, and a coil is wound over there, and that coil is say carries a current of I and having n number of turns. Length is L and cross section area is A. So if the coil is carries a current I and number of turns present in that coil or that solenoid is N, and length L is the mean length of this iron core and A is the area cross section. So that L is basically the mean length of the iron bar and A is the area of the cross section. Okay, this is the mean length of the iron bar and A is the area of cross section. So all of you know that what is the relation between flux density and flux. That relation between flux density and flux is phi is equals to B into A. Okay. And as per Faraday law of electromagnetic induction, we know that E is equals to N d phi by dt. E is equals to N d phi by dt. Now, if you put that d dt of B into A, so that can be represented as N A dV by dt. And also we know that H is equals to what? H is equals to Ni by L. And from that we can able to calculate what is I. I is H into L by L. Because in previous class I already show you that H is proportional to I. Also as per definition, magnetic field strength also is equals to magnetomotive force per unit length. So now power, if you want to represent that power is equals to E into I. That is I, E is represented as N A dV by dt, and I, from these expressions you can able to write that as H L by N, or we can write that as a N cancel out, so that is A into L H dV by dt. Now, if I want to find out that energy spent in a small time, in time say dt, so for that case that should be equals to power into t time, that is A L H dV by dt into dt, or we can write that as a L H dV, that unit is joule. So this is energy spent in time dt. Okay, now we want to find out the total work done, that total work done for one cycle of magnetization, for one cycle of magnetization, that is for corresponding to that hysteresis loop. So that can be represented as work done is equals to AL integration H into dB, that unit is joule. And what is this integration denotes? That integration denotes that integration over one cycle of magnetization.
You are viewing Shobhon Dulalai screen আর view এটা ঠিক আছে.
This is integration over one cycle. And what is that integration H into dB? That is actually called, or that is denoted, that area under the hysteresis loop. Or if I want to define that as work done per cycle, work done per cycle, which is equals to A into L into area of the hysteresis loop. So if you know the area under the hysteresis loop, so from that also you can able to find out that what is the work done per cycle if you measure the area under the loop, under the hysteresis loop, and if you know the volume of the magnetic material, so from that also you can able to find out what is the work done per cycle. And work done means that is the energy loss, that is work done, sometimes also work done per cycle per meter cube, means per unit of volume. So this is simply represents as what? This is simply represented as area under the hysteresis loop. So this one, area of the hysteresis loop, and unit is joule per meter cube per cycle. Here also it is joule per, in this case also joule per cycle also. So this is in that way you can able to find out what is the hysteresis loss for a particular magnetic material. But sometimes it is very difficult, always not Hysteresis loop is always not available, ready-made. So due to that reason, Steinmetz. So there is a empirical formula for the hysteresis loss that is called the Steinmetz formula for the hysteresis loss. You have to remember this Steinmetz formula for hysteresis loss. Okay, what is the formula? That formula is pH equals to kH Bm to the power n V F. Unit is watt. And what is the significance of what is kH? kH constant depending on the type of magnetic material. Constant depending on the type of magnetic material. And what is Bm? Bm, all of you are familiar with this Bm. That is Bm denotes maximum value of the flux density. Maximum value of the flux density. And V is actually the volume of the magnetic material. V is volume of the magnetic material. Okay, and F is known as frequency of reversal of magnetization. F is denote that frequency of flux reversal, you can write in that way, or frequency of reversal of magnetization. And n is known as the Steinmetz coefficient n, and that value is generally lies within the range 1.5 to 2.5, and this is for normal value of n. But for some specific magnetic material, we can assume that as a 1.6 if Bmax lies between the 0.1 to 1.2 Weber per meter square. If Bmax is within the range, so we can write that n as 1.6. Okay, so this is the empirical formula. From that we can able to find out what is the hysteresis loss for a particular magnetic material. সবাই লিখেছো এটা? হয়ে গেছে?
স্যার এনটা কি বলুন আবার বলুন।
এনটাকে বলা হয় স্টিনমেটজ কোএফিসিয়েন্ট। STEINMETZ স্টিনমেটজ কোএফিসিয়েন্ট। ওকে, সবার হয়েছে তো? তাহলে আমি আরেকটা জিনিস ডিসকাস করব, এডি কারেন্ট লস। It is clear to all of you?
Yes, sir.
Now we have to know what is eddy current loss. Just you see, we consider a iron bar that is look like this shape, and a coil is wound in this iron bar and current flowing through this coil. And all of you know, as per Faraday law of electromagnetic induction, some EMF is induced in that material when an alternate magnetic field is applied to that magnetic material. So EMF is induced in the material itself according to the Faraday law of electromagnetic induction. Now you see, so as all of you are familiar with this, that flux is created on it due to that magnetomotive force, if it is Ni, and iron core itself as a conducting medium. So EMF also induced in that iron bar also. So that is the flux that will be linked with that iron core. So because that magnetic material is a conducting material, so EMF circulates a current within the body of the material. So this is basically called the circulating current, and that known as the eddy current. That known as the eddy current. So that eddy current produces some loss in this magnetic material, because magnetic material, say if I consider that eddy current is I, that eddy current I is flowing through the, say, iron core, and that iron core having resistance R. So for that case, some loss is involved due to that eddy current. That is basically called the I square RC, where I is the value of the eddy current and RC is basically the resistance of the core material. Have you got my better? You consider that eddy current at IE, it will be differentiate that I. So you'll understand what I am saying. What do you mean by eddy current and what is eddy current loss? Say suppose an alternating magnetic field is applied to a magnetic material, just a coil is wound on that iron core, and when a current, time varying current is flowing through that coil, EMF induced in the that iron that coil, and due to the time varying current, a flux is generated. That flux is basically most of the flux confined to the core, and that flux is basically created as per Faraday law of electromagnetic induction. That is the EMF induced in the conductor. Okay. Now this flux also linked with the iron core also, because iron core is a conducting material. So that when this flux linked with the iron core, that flux also creates some induced EMF in this iron core, and that core is a magnetic material, conducting material, so some current will flow through the core. That current is basically called the eddy current. And resistance, that particular magnetic material which provides that iron core provides that resistance RC. So eddy current loss for that is equals to IE square into RC. Is it clear to all of you?
Yes, sir.
মানে তুমি যদি এরকম ভাবো যে just you think about that, say like this structure, North Pole and South Pole. So that say flux is created due to that permanent magnetic flux or electromagnetic region. So either this is a permanent magnet or it is a electromagnet. So flux line is created. That flux not only linked with the coil present in the armature core. এইখানে in that armature core some coil is there. If you consider that as a structure like this, so some coil is there, say some coil is there, that flux linked with the coil and produced EMF. Okay, but this flux also linked with this solid iron bar also, and so this solid iron bar, if the flux linked with the solid iron bar and that flux is time varying nature, so what will happen? EMF induced in this solid iron bar, and the solid iron bar equivalent to a closed circuit, so some current will flow through this. That current is basically called the eddy current, that is I suffix C, or better you represent I suffix C. That current is called the eddy current, and that solid iron bar having resistance RC, so due to that eddy current some loss is involved, that is IE square into RC. Now it is clear to all of you which current is called the eddy current. Eddy current is basically a circulating current due to that EMF induced in the solid iron bar. So some current will flow through that solid iron bar. That current is called the eddy current. Sometimes it is also called the circulating current also. And if the solid iron offers that resistance RC, so for that case eddy current loss is IE square RC. But it is very difficult to measure this eddy current in this solid iron bar. There will be no such measurement procedure, or it is very difficult or complex process to measurement of the eddy current. So due to that reasons, some empirical formula again it is there to measure the eddy current loss. That empirical formula is, say this is WE is equals to KE BM square T square F square V. So what is KE? KE is again coefficient of the eddy current. This is coefficient of eddy current, and its value, that coefficient value depending on the type of magnetic material. Okay, and BM is the maximum value of the flux density. Just a minute. So Bm again this is equals to maximum value of flux density in Weber per meter square. Bm is the maximum value of flux density. Okay, Bm is the maximum value of flux density in Weber per meter square. And what is T? T is the thickness of the lamination. I will discuss what is lamination. Thickness of lamination. Okay. And what is F? F is frequency of reversal of the magnetic field, and V is like previous one. V is the volume of the magnetic material. It is clear. Ke is the coefficient of the eddy current, which depends on the magnetic material. Bm is the maximum value of flux density in Weber per meter square, and T is the thickness of the lamination. F is the frequency of flux reversal or reversal of the magnetic field, and V is the volume of the magnetic material. Why we depends on that empirical formula? Because it is difficult to measure the eddy current loss. Now, what do you mean by thickness of the lamination? Say a particular magnetic material, say this diagram is showing a magnetic material like this. কেউ কিছু বলছো? Say if this material consists of a solid iron bar, so for that case effective area will be very high. If the effective area is very high, so the volume of the current is more. So in order to reduce that effective area, we used a very laminated thin iron bar. We use a laminated thin iron bar instead of solid magnetic material. Instead of solid magnetic material, we use a thin laminated bar. The structure is like that. This is a single lamination. So instead of solid iron bar, we use that laminated iron core. This is basically called a lamination. So that is why here it is mentioned that T is the thickness of the lamination. So if you use instead of solid iron, so this one is the solid iron, but instead of solid iron core, if you use that laminated iron core, so for that case effective cross section area is reduced. If you use instead of solid iron core, if you use that 5 number of lamination instead of solid iron core, so effective cross section H reduces to A by 5. So in that way we can reduce the eddy current, so that eddy current loss will reduce. So every time whenever in your machine class, whenever sir discuss about that core as well as stator, and every time they mention that it is made of laminated iron core. Lamination means instead of solid iron, if you use a thin thickness of a magnetic material, that assemble is equivalent to a solid iron core, but instead of a single iron bar, if you use that laminated iron bar, so for that case eddy current loss will be less. Okay, up to these discussions, any doubt? বলো।
স্যার ওই এফেক্টিভ এরিয়াটা বাই 5 হয়ে গেল, ওই পার্টটা আরেকবার একটু বলবেন?
এফেক্টিভ এরিয়া ধরো আগের যে এফেক্টিভ, ধরো তুমি যদি এরকম একটা সলিড স্ট্রাকচার ভাবো, তাহলে তাকে যদি তুমি 4 ভাগ করো, ওকে 3 ভাগ এখানে, তাহলে প্রতিটা ভাগের এরিয়া কত হয়ে যাচ্ছে? A/3।
হ্যাঁ স্যার,
সেইটাই আমি বলছি, যদি 5টা ল্যামিনেশন ইউজ করো তাহলে সেক্ষেত্রে এফেক্টিভ এরিয়া প্রতিটা ল্যামিনেশনের কমে যাচ্ছে A/5। তো এইখানে এখানেও আমরা দেখাতে পারি যে এফেক্টিভ এরিয়া কমলে আমার R ইকুয়ালস টু কি, R ইকুয়ালস
রো এল বাই এ।
R equals to rho L by A। অ্যাপারেন্টলি তোমার মনে হবে কি, যে অ্যাপারেন্টলি মনে হবে যে রেজিস্ট্যান্সটা আমার বেড়ে যাচ্ছে, এখানে ঠিক তাই নয়। এখানে হচ্ছে যে আমার টোটাল কারেন্ট যেটা, সেই টোটাল কারেন্টের সঙ্গে এই ল্যামিনেটেড আয়রন শীটের এই রিলেশন, মানে ম্যাগনিটিউড অফ দ্য কারেন্ট ক্যান বি রিডিউসড বাই স্প্লিটিং দ্য সলিড কোর ইনটু দ্যাট থিন শীট কল্ড দ্য ল্যামিনেশন। এখানে তোমাকে ধরতে হবে that plane parallel to the magnetic field. Each lamination is insulated from each other by a thin layer of coating of varnish. And for laminated core, the area of the each section is reduced, so induced EMF is reduced. As the area through which the current is passed is smaller, that resistance of the eddy current path also increases. Effective resistance of the eddy current path increases. তাহলে effective area of eddy current path is increases. So we know that V is equals to I into R, or I is equals to V by R. তাহলে effective area of the resistance eddy current path যদি increase করে, তাহলে eddy currentটা আমার itself কি হবে, decrease করবে। বোঝা গেল কিনা?
হ্যাঁ স্যার।
সেইভাবে হচ্ছে যে আমার এডি কারেন্টের ম্যাগনিটিউডটাকে ডিক্রিজ করা হয়, সো দ্যাট টোটাল লস ইন দ্য and every times that eddy current loss and hysteresis loss, they are not actually required, or that is not used as a useful power of a particular electrical machine. Okay, so that is why always our tendency is to decrease that either eddy current loss as well as hysteresis loss. You have to decrease that both the losses. But sometimes that eddy current loss is useful. Maybe in your case it is not required, but as an electrical engineer, that eddy current loss is sometimes is used for some other purpose. Have you familiar with say term induction heating? So that in case of the induction heating, that eddy current loss, that principle is used for induction heating. And when we will discuss about that some measurement circuit, in that circuit also one of the torque, that is the damping torque, also provided by this eddy current loss. And sometimes eddy current loss also used for detecting the crack in the metal parts. Say suppose in metal parts, say this is a solid iron, if metal parts inside there, if there is any crack is there, to determine this crack, that eddy current loss or eddy current principle is used for measurement or detection of the crack inside the instrument. Okay, but in your case you have to know what is the basic principle of the and why the eddy current loss is occurred in the magnetic material, and why hysteresis loss is occurred in the magnetic material. Okay, if you have any doubt still, কোনো ডাউট থাকলে বলো, নাহলে আমরা একটা প্রবলেম সে যাই।
না স্যার ঠিক আছে।
ওকে, যদি ঠিক থাকে তাহলে আমরা এরকমটা করি। Okay, you write for one problem, numerical problem. The hysteresis loop, I am writing as a in brief, that is hysteresis loop of a sample of sheet steel hysteresis loop of a sample of sheet steel subjected to Bmax 1.3 Weber per meter square has an area of 93 centimeter square. এটা হচ্ছে হিস্টেসিস লুপের কিন্তু আমরা এ দিচ্ছি। স্কেলটা কি? স্কেল হচ্ছে যে 1 সেন্টিমিটার is equals to 0.1 Weber per meter square and 1 centimeter হচ্ছে যে 50 ampere turns per meter. এটা কার স্কেল? হিস্টেসিস লুপের স্কেল BRH. Now you have to calculate the hysteresis loss. Calculate the hysteresis loss in what? When 1500 centimeter cube of the material is subjected to an alternating flux density Bmax 1.3 Weber per meter square, peak value of frequency 65 Hz. এইটা হচ্ছে তোমাদের প্রবলেম। তাহলে as per derivation, loss is equals to area of loop, that is joule per meter cube per cycle. Okay, so area of loop, how will we find out area of loop? So for that purpose you have to consider that scale 0.1 into 50. So that is basically represents what? That is the area. And what is the actual area for that? 93. So that is into 93, which is equals to 465 joule per meter cube per cycle. Now volume is given 1500 centimeter cube. Okay, and number of flux reversal, that is equals to frequency, which is equals to 65. So actual hysteresis loss, which is equals to, that is 465 joule per meter cube per cycle. If you multiply that by volume and by cycle, so you'll be get total loss. So that is 465, volume is 1500 centimeter cube. It will be better represent it in 1500 centimeter cube, that is 1500 divided by what? 100 to the power cube, that is 15 into 10 to the power minus 4 meter cube. So which is equals to 15 into 10 to the power minus 4 into 65, that is joule per second, and which is equals to, তোমরা ক্যালকুলেটরে ফেললে যেটা পাবে সেটা হচ্ছে যে 45.3 watt. 45.3 watt. So in that way you have to solve this. Is it clear that solution? দেখো সলিউশনটা ঠিক আছে কিনা?
স্যার
আরেকবার বলবো, তাই তো? দেখো এখানে দেয়া আছে হিস্টেসিস লুপ অফ এ স্যাম্পল শীট স্টিল Bmax 1.3, এরিয়া হচ্ছে 93। তাহলে এরিয়া ইজ গিভেন এবার এর স্কেলটা কি পার সেন্টিমিটার 1 সেন্টিমিটার আমার তো বিএইচ লো জাস্ট ইউ থিঙ্ক অ্যাবাউট দ্যাট বিএইচ লো এর এরিয়া আন্ডার দ্য কার্ভ দেওয়া আছে হচ্ছে যে 93 কিন্তু অ্যাকচুয়ালি লস পেতে গেলে আমাকে কি করতে হবে 1 সেন্টিমিটার 1 সেন্টিমিটার সেটা দিয়ে মাল্টিপ্লাই করতে হবে তাহলে দ্যাট উইল বি ইকুইভ্যালেন্ট টু that energy. So due to that reason we have to multiply that 93 by 0.1 that is B into H into 0.93 so that is basically provide joule and B is 0.1 Weber per meter square and H is 50 ampere tons per meter so you will get that loss per cycle per unit volume that is 465 joule per meter cube per cycle. And to predict the total loss, mind that this is actually the total loss. So how you will get total loss? For that, this is loss per unit per volume per cycle. So you have to multiply it by the number of cycle or number of flux reversal that is 65. So that will be vanishes. Then you multiply that by volume. Volume is given 1500 centimeter cube that is 15 into 10 to the power minus 4 meter cube. And ultimately you will be get that this is the total loss. Is it clear?
Yes, sir.
Okay. আর কারো কোনো কিছু ডাউট থাকলে বলো